Apollo 11 turns 50. Exploring the moon yesterday, today, and tomorrow. I'm Tonya Hall, and joining me is Dr. Noah Petro, project scientist for the Lunar Reconnaissance Orbiter, NASA's Goddard Space Flight Center. Welcome, Dr. Petro.
Oh, thank you for having me on.
What is the LRO and what's your involvement with the project?
The LRO, the Lunar Reconnaissance Orbiter, is a spacecraft that we launched in June of 2009. It's been orbiting the moon since then, so 10 years at the moon. It's the longest lived lunar spacecraft, orbiting spacecraft of all time. And I'm the project scientist for that mission. Now, what does that mean? Project scientist is kind of a catch-all for several different responsibilities. We have 7 instruments on the spacecraft, and I am responsible for making sure that the 7 instruments play well together. We have several responsibilities to NASA to deliver our data on a regular basis, to periodically check in with NASA to report how we're doing. So I'm the lead scientist for the mission, making sure that we're doing the things that we say we do, but also to respond to NASA headquarters questions, concerns, to make sure the mission continues to fulfill its obligations, both for science and exploration purposes.
We just celebrated the 50th anniversary of the Apollo 11 moon landing. Mm-hmm. How is NASA looking back at this monumental human achievement?
Yeah, so NASA viewed this Apollo 50th anniversary as an opportunity to really reflect on what we did then, the amazing undertaking it took to land those brave astronauts on the lunar surface and bring them back to Earth. But also to remind folks that we brought back 48.5 pounds of moon rock with them. And then that opened up a whole new era of scientific exploration of the solar system. And so it was this opportunity to look back, reflect, I think also look at where we are right now with lunar science, with planetary science, and then look forward to the future plans with the Artemis program of returning humans to the moon by 2024. And so, NASA tried to take advantage of the intense excitement and interest in Apollo 11 and really use it to our own advantage to communicate, again, this wonderful achievement, what we learned from it, and what we want to do going forward.
As you mentioned, in the next couple of months, NASA will be opening up these moon rock samples that were sealed since the Apollo missions. Why did we wait so long to open these, and what do we hope to learn from the samples?
Yeah, these, quote, pristine samples that we'll be analyzing was a real kind of forethought moment back in the Apollo era, that there was a recognition that the analytical techniques that existed then would be superseded in the future. And so there was a set of samples that were collected under very special circumstances on the moon and that were preserved, basically untouched for 50 years so that they could be studied at some point in the future. Over the last several years, there was this development in lunar science, identification of lunar volatiles, many new science questions that we really could not ask or answer 50 years ago. And we've gotten to a point now where the techniques, the capabilities, our instrumentation have progressed far enough along where we can ask really leaps and bounds, more detailed questions of the samples, particularly very small fragments of samples, than we could 50 years ago. And so now there's an opportunity for selected teams to be able to analyze a few of those special samples. We're not opening or touching all of these pristine samples. There's some that will remain pristine for further future generations. We're opening and touching, I think, 2 of the selected samples that are, quote, pristine. And so starting in September, there will be the first analysis of some of those samples, some of the samples that were collected, not touched, but are in, let's just say, easier to analyze. There's a set of samples that were taken from a drill core that was actually sealed on the lunar surface. So in theory, if that seal is held over 50 years, any gases that might have been on the lunar surface or inside the regolith, the uppermost surface of the moon, we can analyze those samples. We're not going to analyze that special sample just yet because it's going to require incredible attention to studying what might be in that core tube. There's a portion of that core tube that was collected that wasn't sealed on the surface, and so it has not been looked at for 50 years, or just under 50 years since it was collected in 1972. But that sample, which has never been analyzed, will be studied first in the coming months.
You mentioned that the LRO just celebrated its 10th anniversary.
Yep.
What have we learned in this time, and what have been some of the surprises?
So I think for me, one of the most impressive things that we've learned is really how dynamic the moon is. And you may not think of the moon as being a dynamic object, But because we've been at the moon now for 10 years, again, longer than any prior mission before, we can actually see the moon changing underneath our spacecraft, underneath our feet, if you will. And so we've been able to identify new impact craters, surface changes that have occurred. We've seen the presence of volatiles vary as a function of time of day. So we're seeing how the moon operates on a very human time scale. I've never been able to do that before, and so for me that's really exciting. It's very compelling because it shows us what the moon actually is doing in response to the environment that it's around. So for instance, we are able to understand how the moon responds to micrometeorite bombardment and how the surface of the moon is changing over relatively short time scales. We've never been able to do that before. That's important because if we want to go to the moon and have an extended presence there, we're going to want to know what the hazard is for having a meteorite strike your habitat, or having a meteorite strike 100 kilometers away, but ejecta from that impact hitting your habitat. And so we're actually able to see the rate at which the surface of the moon is changing. And the longer we're at the moon, we get obviously better statistics for that and really improve our understanding of how the moon responds to being in deep space. I like that from a very personal connection because here on the Earth, because of this wonderful atmosphere that we have that allows life to exist here, we don't get a really great sense of what the environment is, the micrometeorite environment is in our corner of the solar system, whereas we do get that on the moon. And so, the idea of using the moon as a natural extension of the Earth, in the same way we use what we do here on the Earth to understand how planets work, we do the same thing at the moon. And that reinforces in my mind the connection between the Earth and the moon as not really two totally separate objects, but really as partners in this whole crazy thing we call everyday life in space.
One of the LRO's goals is to search for subsurface water deposits. Mm-hmm. Tell us about the MiniRF technology behind the search.
Yeah, so we have a really interesting instrument on LRO called MiniRF. It's a radar instrument. Initially, when it was first in orbit, we were able to basically send radar waves from the instrument to the lunar surface and back and measure it on our spacecraft with the instrument. Several years ago, the transmitter that sent that radar pulse to the lunar surface broke. And so instead of abandoning this instrument, we actually developed a new technique for using antennas on the Earth, first the Arecibo antenna in Puerto Rico, to essentially illuminate the lunar surface and use MiniRF to measure the reflected radar beam off the surface from Arecibo. We now also use a telescope, an antenna out in California with the Goldstone complex out there to do a similar measurement at a different wavelength. And so it's a new measurement, a totally new type of measurement we didn't envision when LRO was launched, that allows us to peer a meter or so below the surface to look for the very diagnostic wavelength responses that ice has. And indeed, we've identified one location near the South Pole, near the L-Cross impact site, as a matter of fact, in Cabeus Crater, that has a very diagnostic signal for water ice. So we use MiniRF data as well as data from really the 6 other instruments to try to constrain where we think water and volatiles might be. What's really interesting about all these measurements is that we see some areas where there's a consistent signal of water ice or water, and some places where it's an inconsistent signal. And that begs us the question, why is there that inconsistency? And that's where science comes in, because there's a hypothesis to be tested there and something for us to investigate.
So then explain Artemis, NASA's next mission to the moon. And you mentioned the South Pole. So why is the moon's South Pole so interesting?
Yeah, so Artemis is the next program. Artemis being the sister to Apollo is going to be the set of missions that will get the first woman and next man to the lunar surface as early as 2024. Very excited to see basically our LRO observations ground truthed. Having astronauts actually go and investigate the areas that we've been exploring. We're interested in the South Pole, and indeed the poles in general at the moon, because we know those are unique environments. The poles of the moon have these wonderfully permanently shadowed craters, areas that receive no direct sunlight. And so we know that those areas can be very cold and harbor some very interesting environments. Some of those permanently shadowed craters have water or volatiles in them, some do not. And indeed, there's some illuminated areas that have volatiles in them as well. So there's a real dynamic and interesting environment that we've discovered at the South Pole of the moon. And that's what's sort of begging us to explore. In the wake of Apollo we know that the moon is an interesting place. We also know that Apollo explored a very limited area along the near side, equatorial region of the moon. And so we're building upon those successes of Apollo by going further than Apollo could go, and namely to the south pole of the moon. And from that, we'll get insight into not just the volatiles history of the moon, but indeed the whole geologic history of the moon as recorded there at the south pole.
Dr. Noah Petro, project scientist for the Lunar Reconnaissance Orbiter at NASA's Goddard Space Flight Center. If somebody wants to connect with you, maybe they want to find out more about your work, how can they do that?
The NASA website has tons of information. I'm obviously more attuned to the lunar side of that. So if you go to moon.nasa.gov, or for the LRO mission, our website is lunar.gsfc.nasa.gov. But you can always, as the kids say, hit me up on Twitter. I'm NEPetro that's it, NEPetro. That's my Twitter handle. There are a number of Noah Petros out there. I'm the only Noah Petro at NASA. So if you find that Twitter account, that was likely me, until there's an imitator, a Noah Petro NASA account, or which I don't think has existed yet. And I pity the person who decides that that's a good idea to do. But I'm always interested and excited to try to answer questions. I think it's really important that people who are curious about lunar science, about planetary science, get their questions answered, and I'm always happy to do that. Of course, another good follow is the NASA Moon Twitter account that we run here from Goddard, and is a font of all things in lunar for enthusiasts.
I love it. Thanks so much again. And if you guys want to find more of my interviews, you can do that right here, or go to tonyahall.net. Thanks for watching.